lambda goes to infinity, that's the regime. It gives us a semi-classical limit. If you send lambda to infinity, this is what people call a semi-classical limit, right? And this is studied by Barry Simon. I think it was a paper of 1985, Annals of Mathematics. So he basically investigated this operator. So he started a similar like this, and he studied the eigenfunctions of this operator. Just as a side remark. So we discretize. So we take this operator basically as a starting point, right? We discretize it. You can discretize the grid, the space. This delta, you should think about the grid spacing, and then you get basically this out of it. And now is the idea. You have basically two ideas. You see their lambda, you see their delta. They are basically not related to each other. The limit delta goes to 0 gives you the continuum limit, lambda fixed. The limit lambda to infinity gives you the semi-classical limit, delta fixed. What's this? Okay, so this goes two a priori different regimes you can get out of it. The interesting case is, what if this lambda, the semi-classical limit, this lambda there, is somehow related to the delta there, so to the spacing. And that's the interesting case. And that's what we're basically going to do here. So we couple the parameters delta and lambda, right? We send delta n as 1 over n. That makes sense. You take a uniform grid spacing, a lattice point, a lattice ZD, and you say, okay, my scaling is 1 over n, uniform grid spacing. And lambda n is given by this kind of function here, n to the power 1 minus gamma. And now one can ask, okay, this is a choice, and with this choice you get this operator out of it. If you remember here the definition, delta lambda becomes now 1 over n, that is the delta, lambda is this. You get this operator out of it. And this is now, you have to make a remark, because this scaling here, which you see there, is a choice. One could say, maybe you take a different scale, you take lambda n as exponential of n or something. Is a different choice. There are here infinitely many choices possible. It's a very open question how to do this, if you scale this here with a different function, so not in this way, what then the asymptotics will be. That's unknown. This is a kind of idea which is kind of makes sense in my opinion. Rodrigo, I don't know what happens all the time. Okay. Okay, so this operator now is seen as a, so this is our object now, and then we can rescale it towards an operator we can rescale it as an operator here, and we get this. This is just the same. Those are unitary equivalent. So it's just saying I take my operator on L2 Z of D, or I take my Z of D divided by n, right? It's just a rescaling, and those are unitary equivalent. So one can see it like this, or one can see it on L2 Z of D, which is maybe a bit more natural. You can see it like this. It's the same identically thing, and here's exactly what I wrote down. Vn of x is just Vx divided by n. So this is now our model. We go to study, and so we go to analyze this model for different values of gamma, and go to identify spectral asymptotics for this model. Also implementing. Yeah. Let me see this. Maybe this is a typo. This should be. So you mean this one, the green, the orange one? So is it this? This is. I think this is correct. Yes, because we are on L2Z of D. But then you say Vnx is Vx over n. So that you come continuously close to each other. Yes, but this you have to. I think this you have to anyway implement here. This kind of thing. Here's V of x, and this V of x is a potential on basically on ZD divided by n. So you have to think, so x is a point, you think this is correct, x is a point on Z of D, Vn of x, you have to scale it like this. So if you think about x scales, so the idea is that x here as a point of Z of D is like, it scales with n. It could be a sequence of numbers in Z of D, which is like n times a fixed x, and take the floor or something. If you then divide by n, then those points are coming dense there. It says, you should see it like this. So this x is fixed, but it could of course be that x is n times a different point. Right, and then x times divided by n will localize. You see it like this in the sense of a sequence. So x.
The domain should be not the integer number or not. It should be ZD or not. The
no, x. This is an integer, and you divide by n. Yes. So x could be perfectly n times another x, right? Could be a multiple of n. This could be a multiple of n, you divide by n, so then it will not go to 0 somehow. It will kind of stabilize. And here not, because here you are by definition you are here inside the quotient. So again, this work has been studied by several researchers. So if gamma is smaller than -1, I go to give you a short picture of this, because it's very illustrating. If you just write it down and see then what happens. So for the moment I take a second Vn of x is x harmonic oscillator. I take just this here. X is here in my Z, in my line. Take also D as 1, doesn't really matter. We take one dimensional just to illustrate it. So gamma -1, smaller than it was, I think the first was smaller. We have Hn is basically given by n squared, the discrete Laplacian, plus, there's just a computation one can do, x squared f, right? This is already there, so it's f to be here. But this is what you see here. If you do it like this, you get this kind of. You can rewrite this in this way. My operator, the one written there. Plug in the harmonic oscillator. You play a bit. You can get an n squared out of the brackets. That's important, because if you now look to this object, if gamma is strict less than -1, you see that this thing here, so forget about this, and there's a prefactor, doesn't play a role. You see that this object, this is positive. If gamma is strict larger than -1, this is something like this goes like n to a power alpha. So this is again a semi-classical limit. You see here, n blows up times the potential. So this object here behaves like a semi-classical limit of a discrete Schrödinger operator. So this is a semi-classical approximation of a discrete model. Discrete Laplacian, a thing that blows up. This was what Simon had. He had a continuous one. Right? This is the idea if gamma is smaller than -1. If we say, take gamma is -1, we have those different regimes, you get basically, if you can do a similar computation, you find x squared. Here you see, divide by n, this is a prefactor, I repeat, it doesn't play a role. Here you see, no semi-classical limit, no continuum limit. This is just a purely discrete model for gamma is -1. So you get here a discrete model. You just get a discrete model, and there's no limit to take basically. There's a different asymptotics for this gamma. If you now go, forget about 1 second. This was an illustrative idea for the gamma is -1 and 1. If you now take gamma in this interval here, right, you get, if you take this equivalent characterization on the quotient, so on L2, on L2 ZD divided by N, you see something like minus a half. Maybe this minus is you get something like F X. It's just a matter of writing everything down. Squared plus, there was still this potential, right? So this, what was it? In this case, is it lambda n squared v of x, whereby v yet in the quotient, zd divided by n. So what you see here, there is no splitting. This n squared, what we've seen before, cannot get out in front. So we see here, you get here the Laplacian continuum. So if you do the analysis and you, this, heuristically speaking, this goes like V, basically, right? So this is what Barry Simon, that was his regime. We have a continuum Laplacian plus something that blows up times the potential. So in this regime, you recover the semi-classical limit as you would have started from the continuum Schrödinger operator in the semi-classical scaling. So that's a different regime. It's not related to the previous one. If you know a bit more, you can do. If you go to gamma is +1, you get, as a similar as I said before, you get this plus lambda. So remember, 1 minus gamma was a squared v. So this gamma is 1 is gone. So you get just the continuum limit. So for gamma is 1, this is just continuum, basically how you say it, limit. So the asymptotics you expect of this operator to behave like as if you would have started from the standard Schrödinger operator without any semi-classical scaling. Gamma is 1. If you now go one more time, you go say gamma is larger than 1, than +1. If you go back to what was written here, n 1 minus gamma, maybe there was a square. If gamma is larger than 1, then this thing effectively goes to 0. Of course, v has some features here. Eh? If this goes to 0, what you then get, you get the free Laplacian. So all those different scalings of gamma, it can really identify here 5 regimes, and just doing some hand-waving arguments, you can indeed see that there are 5 different regimes. The free Laplacian has a completely different spectrum as this one, of course. So that is basically the idea why we identified those regimes, or how this came out of it. And this was a little bit a short story. And yeah, so some people, so now go back to the literature. So who has worked on this works? So again, maybe it's this.
No, this is just what here is just a song. What happened is with technical problems.
Maybe the battery is finished.
No. This is just to pass. I mean, what is happening is here. I have to. It's the cable there. Maybe you are touching the cable.
Maybe I stand on the cable. You think? It could be. Yes, it works. This is cable. Very good. Yeah.
Maybe if you touch that, we can interfere.
Yeah, I don't touch it anymore.
Okay, don't put this.
Okay. Yeah, so going back to a bit literature. So this gammas minus one regime has been studied. So the semi-classical approximation of a discrete model, the first thing I showed, by, for example, Bach, Walter de Pedra, and some other people, they've studied it, but not exactly in this kind of setting. They had different. They got slightly different models. But this is basically the idea I extracted from the literature. Gammas minus one is a purely discrete model. There is also literature, but it's not so interesting because you basically have just a discrete model, so this can be anything. Gamma S minus one is the most interesting case. It had a semi-classical approximation, like you would have started from the Schrödinger operator on RD. That one, Simon basically started with this one, and we recovered this asymptotics. So gamma 0 is studied by Helva Sjöstrand, basically one of the first ones who started this discussion. Kamioka, so I think Japanese professors also have worked on this. And then there is this group, Markus Klein and Elke Rosenberger. They work both in Germany, in Potsdam. I think Markus Klein is retired, but she is still there. They did this kind of regime, not exactly from the same operator, but in a slightly similar context. Gamma S1 is the continual limit of Hn towards this operator, right? No semi-classical, purely continuous model. This is studied also by the Japanese professors. Interesting how they get this. And then there's when gamma is larger than 1 is basically uninteresting because you just get back your free Laplacian. That's not that interesting. But there's a regime you have to take into account if you want to take all the gammas. And so those 5 different regimes are there. So now I didn't say so much about my potential because of course not any potential will work here. For not any potential the spectrum will behave well. So I take my potential smooth on RD and positive. It doesn't have to be positive, it can be bounded from below, but you can just assume this, otherwise you scale it. You add up a constant. You say that V has zeros, A1, AM, and then you have to assume that the Hessian there is strictly positive definite. This assumption maybe sounds strange, but this is kind of polynomial potentials like a double well or harmonic oscillator, they satisfy this. So in order to make it work for any regime, we have to take such a potential and a strictly positive at infinity. That is also a technical assumption you want in order to estimate the tails of the. If you have to prove convergence, then you have to implement some approximate eigenvectors, and this is kind of important to get rid of errors. But based on this assumption of V2, basically, you can say that the Hessian has strictly positive eigenvalues at 0, right? Omega is omega I A L. For each I and each L is 1 over M. So those are the zeros. So M's are the zeros. So you have different Hessians, more Hessians. And then we can define this set. This is just, what is this? This is just basically the set of energy levels. You can introduce them in such a way, and you can count them also. This is just counting, right? Say they depend on V, of course, on the potential, and you can count them in this way, right? And those energy levels, if you know, this is not done completely random. This is done a bit on purpose because we were inspired by the paper by Simon, and those are exactly derived from the semi-classical limit starting from this one. So Simon, remember, started with this one. So this lambda n there was basically n is 0, so he got just n squared. Right, and he got the spectral asymptotics, and it was exactly coming this kind of ideas. So we generalize it from a discrete model, and then recovering his results, and only in this regime, gamma between -1 and 1, but extending it also to other regimes. So this is the idea about the spectrum, the eigenvalues, and then the first theorem we proved here is if you assume V to have those assumptions, right? Then, if you then take the nth eigenvalue of the operator Hn, Hn is our discrete Schrödinger operator. Remember, spacing and semi-classical parameter are coupled. Then for all n, for each natural number and each gamma in the head is the semi-classical regime, we get convergence. We can prove that the eigenvalues of this semi-classical to continuum coupled Schrödinger operator divided by lambda n is actually convergent. And this proof is not so easy. It's very technical, so I give you just a short overview of how to do this. So for the harmonic oscillator, so this holds, this holds for this potential, basically satisfy these assumptions. If we now to extend beyond this interval, so the minus infinity to -1 and 1 to plus infinity, is a longer interval. You can do the same. Then you have to basically go to a harmonic oscillator. Remember, this can also be done for more generic potentials, but it won't bring more. The paper will become much longer, which is actually not insightful anymore. So we focus here on a harmonic oscillator, and then we know if this is a fact. Harmonic oscillator and the continuum has a purely discrete spectrum, and we can prove that. Remember, this interval goes from -1 to 1. If we extend it to infinity, then for at least for the harmonic potential, then we get exactly the same, basically. It's just it, but now we have a harmonic oscillator. We can extend the interval. It was just an extra information we want to prove. However, if you now go to the other part of the interval, right, minus infinity to -1, included -1, so in 1D, I mean, this doesn't really matter, just for convenience. You can find also these operators here, and then you can prove that for gamma is -1, you just recover, you see if gamma is -1, again as a prefactor n squared in the front, can be kicked out, and you just get back the spectrum of your operator H1, like there was only a 1, right? This n squared, if it is factorizes, it doesn't play any role. So you get this back. However, the interesting case is here, if gamma is really strictly between -infinity and -1, so not -1 itself, but strictly in between, then you get this kind of semi-classical approximation of your discrete model. So that's indeed, is this what I... So if gamma is, then you get the semi-classical approximation. So this is what I tried to say before. For the harmonic oscillator, you can see it. So you get kind of this regime here. This is then the limit of your, basically of your spectrum. So it all converges. And I think it's quite interesting to get this. Remember that for the operator, Schrödinger operator itself, in the quantum, it's clear because you know your eigenfunctions, you know your spectrum. That is all clear. But in the lattice case, it's not clear. The spectrum is not directly known. You don't say it is the Hermite polynomial. It's much more technical here. So we use basically the Hermite polynomials of quantum to reach this result by approximating, etc. So let me just sketch you shortly the idea of the proof in 1D. Harmonic case gamma -1 to infinity. So I'm speaking here about this regime here. So how to do this? It seems maybe easy, but it is actually not, except for the upper bound. So you have to do a suitable scaling. Forget about how this all is defined. It's just the idea is you have to introduce a scaling with a modified harmonic oscillator. And then with test functions, you can approximate the eigenfunctions of this scaled harmonic of this modified harmonic oscillator. And so you have first your harmonic oscillator, you modify it by the scaling, and then introducing suitable test functions. This H are the Hermite polynomials, so that's why they come back. You can approximate you can prove that psi n are approximate eigenfunctions, so modulo an arrow which vanishes in the limit. That means approximate here. So and then you can also prove that those psi n are almost orthogonal. Again, modulo an arrow which vanishes in the limit as n to infinity. And from this you can get the upper bound. So remember, this here is exactly, and d is 1, omega divided by 2 to n plus 1 is exactly, basically, what this means here. So you go here, wait. So a half omega 2n plus 1 is basically what we then prove here. So this is in 1D, it's just the upper bound. If we now go to the lower bound, that's very complicated. The upper bound is often, one of the two is always easy, and then the problem is here. So how you do this lower bound? Then you have to come up with some other idea. You cannot approximate. You can use approximate eigenfunctions, but you have to do something more. And there is known as Akmon-Allegretto-Piepenbrink theorem. That what it does, it connects basically the existence of positive superharmonic functions to lower bounds on the ground state energy for some suitable alpha. So what does this mean? A function, do it in 1D here, is basically called alpha superharmonic for an operator if you have this kind of relation here. If h plus alpha multiplied by the function itself is larger or equal than 0. It's called harmonic if it is exactly 0. So the ground state would be harmonic as an example, but this is a slightly more general notion. And then the theorem says, of course, U should be, I think, also positive. U should be positive. Forgot to write it down. The theorem then says, if you take the ground state energy, right, then the following are equivalent. It holds that alpha is larger than this minus the ground state energy. And this is equivalent to saying there exists a strictly positive alpha superharmonic function. And this kind of theorem will be used to construct somehow or eigenvalues. Oops, sorry, shit. Okay, no, okay, good. Yeah. So this theorem will be used to construct this, and that will become clear now. I mean the sketch. So the problem here is still the Akman-Allegretto-Pipelman theorem applies only to ground state eigenenergies, but we had a theorem for all energies. So how this possible? A priori, when people says, okay, you can have nice the ground state eigenenergy, but the second, first, third, who knows? So the idea is to the higher eigenvalues, you can restrict Hn to nodal intervals defined with respect to the zeros of a metapolynomial. So those are polynomials on the line, they have zeros, and you can restrict your operator basically to those intervals. You get on those intervals, you can define restricted test functions. You can restrict everything basically to an interval, and on that interval, right, you can view it as like it was the ground state. So you have your operator restricted, and then you can apply the theorem to those test functions, and they are then behaving like a ground state only on the restricted sense. So you can apply the theorem, and you get restricted eigenenergy. So you get a very nice here. You see already here some lower bound. Those are not yet the energies we are interested in. Those are not yet the operators we're interested in, but this is just an approximate model which a priori has not so much to do yet with what we want. But then you can patch this whole thing together. It's a very technical story. You can take the minimum of all those energies. You can glue the intervals together, which is a story I'm not going to explain here. And that basically gives you a global test function for which we have this inequality. And if you then take the lim-inf, then indeed you can get the lower bounds. So that's basically the idea of doing this. It's only still a harmonic oscillator. So there is not yet the potential we are actually interested in at the beginning. Still a harmonic oscillator. So how we now, having done this, how we now can kind of, so the theorem basically was, here, this V is not a harmonic oscillator. So we have not done prove this for the harmonic oscillator. We want to kind of go beyond. So for general potentials, you can again approximate Hn around the minima by a harmonic oscillator. Right? Think about the Taylor series. You get this minima, they behave like a harmonic oscillator. And outside the minima, so if you are away of the minima, that's a ball of radius depending on del on n, then it's basically you can prove that there's a decay. So what only counts here is basically the behavior around the minima, which is like a harmonic oscillator. And then how you do this then you have to kind of use the EMS, the Ismailov-Morgan-Simon localization formula, which is quite well known in quantum mechanics. In discrete sense, it's not so well. It's more like in a continuum. For discrete models, it's not very well known. It's a quite technical. It's basically said about this. If you take a sequence of functions here, right, sum up to 1, square sum up to 1, and for any bounded self-applied Laplace type operator and potential V, if you write like this, you have this kind of decomposition of H, your Schrödinger operator is the idea, in terms of this kind of decomposition you have, and you can prove that this commutator here has a bound. So that's the idea. And the first term is basically you think about the energy, and the second term is a controlled error. So in our case, we can make this controlled error going to 0. So this is what it is, and this formula, without going down into the details, is the trick used to get to the estimate for general potentials, not only for the harmonic oscillator. And now we have this was basically the sketch of the proof. So what is this here? So if you now go to this theorem, you see this graph. And this is the spectrum, log of the spectrum divided by log of n, as a function of gamma, right? This is the gamma. And what is this here? Just to make to show you a second what is this kink there at -1 is coming from, I will just give you this clear. So gamma is -1. Then you get a bit idea what this actually means. So we get H, the energy, right? N. This is proved in the theorem set that Hn. Just set that this goes like n squared right. So if you take the log of this, you get basically 2 n squared log 2 2 log n plus log En small n h1. This was this operator. We divide by n, and here you also then divide by n. So this cancels. So this is 2, and this here goes to 0 because this is small n. This is not n capital N dependent. This is 1. This is not. This operator is a Schrödinger operator for n is 1. So this cancels. So you get exactly 2. So in such a way you can compute this whole story here. So that's exactly why -1 you get 2. And then you get some continuous decreasing in a semi-classical regime, and then it goes, so gamma is larger than +1 is not that interesting because you get the free Laplacian. So that's not interesting. So we get here this kind of graph, if you wish, as a function of gamma. So now I'm going to tell you something about the second work. So if you have questions about this, please let me know. So we have seen now, we have characterized here in this context the spectrum of this potential type we have just seen in -1, 1, and for the harmonic oscillator we have done it for any basically gamma. So now we focus only on the regime gamma is -1, 1. So this is the semi-classical regime, the interesting one. And if you now first go back to the continuum case, the one Simon studied, this one. And now you assume you have 2 minima, A1 and A2. So if you then think about what is this basically for kind of potential, then you see, you get here, you can see it as double well potential. So that is something typically fitting in this. It's not all of them, but this is typically an idea, a potential which is taken into account. Okay, then you get 2 non-degenerate grounds. You get a non-degenerate grounded eigenvector. This you can prove. It's discrete. It's not so complicated to prove this. And if you now define this metric, the so-called Achmon metric, so it's defined in terms of the potential. This is invited by Achmon. I think he Israeli mathematician. I'm not sure if he's still living, but he kind of invented this type of metric, in which you then somehow so the points are related to the potential. It's kind of this idea here. This density is basically the potential itself. That's quite famous among people in Schrödinger operators. So this Achmon metric is a distance defined in terms of the potential itself. If we do this, then Simon proved 1984, 85 in a semi-classical limit, so as lambda to infinity. Remember, this is the object. That the ground state eigenvector, if you then this is positive, so you don't have to take an absolute value here. In the point x, depending on n, remember this n is just an index this n is this lambda basically, it's this scaling. So I should call it here lambda. I apologize for this. That this here the ground eigenvector satisfies this kind of identity. So if x, so it is basically related to the minimum of the Achmon metric. If the point x related to one of the minima. So if you are here right from A2, then the minima is given by this one. So then this is the minimum distance. If you are very close to here, then this is the minimum distance. So this is a very interesting result which says that the ground state, so that this basically implies that omega 0 xn goes like E minus n, or minus lambda, I mean lambda is n in this case, times this, let's say times this function I. And I in my case is this minimum. So Ix is minimum things like this, right? So that is what exactly means when you're having a large deviation principle. But the rate, this is my rate function. So it behaves like in decaying. Of course, if you're at the minima, if you are at a 0, then this is 0. And then you have basically nothing there, you localize. So that's the idea of Simon. And we want to recover this. So what is the idea in our case? We fix, again, as seen before, this is now our regime, our operator. Again, assume 2 minima of our potential. Can do exactly the same. And try to ask us, what is this asymptotic behavior of our discrete eigenvectors, Crouched eigenvectors? Can we expect this? Oh, sorry, I forgot also to say that this is the spectral gap is basically saying that it converges to the spectral gap in this sense converges to the argman, to the distance between A1 and A2. So that is this tunneling. That is not an upper bound or lower bound. This is an exact limit. Barry Simon proved it in this paper. Very nice paper. Technical but interesting. So we want to do a similar thing. We want to see, hey, starting with a discrete Schrödinger operator, scaling gamma, what one can expect here. Do we get a similar asymptotics here? If diving into the literature, you see that Klein and Rosenberger, Kamioka also, they didn't do this. So they studied similar models, but they invented another metric, so-called the Akmon-Finsler metric, which is not, this is not the same as this. It's a completely different metric. It's a very technical proof, and they proved that the ground state eigenvector, so this one here, is smaller equal, so you get only upper bounds. And then we were thinking, but why they studied only this metric? Why they didn't start directly with the Akmon metric and try to recover this? Then it would have been identity. Indeed, that's what we do. We use not this metric, because this metric is actually it's not sharp. If you go back to the Akmon metric, you get exactly a limit. So we proved that this is now almost an archive, but there is no need for this Akmon-Finsler metric. We proved that exactly you get recover Simon's tunneling rates, tunneling and a large deviation principle for the ground state. And so nx is then basically take the floor, because it should be a point, of course, and it should be a discrete point. And we get this out of it, and yeah, that's I think an interesting result. We have now it for DS1, but we want to generalize this to arbitrary dimensions, which is still a bit a pain because there's some technicalities. Then I want to say last thing about possible extensions. So the Laplacian we studied here in this work is always a discrete Laplacian without any edge weights. You can think also, I take a Laplacian, so I take basically, I introduce a function like B, symmetric function, and you define your Laplacian in terms of this function. So the edges are weighted by this. You get a Laplacian, a sum, right? You get it weighted by a graph, right? Edge weight. And this is an idea which is much more complicated, because then each edge has a different weight. And in our case, always were the same. So this is a thing we want to, you still think how to do this. You can also do this related to spin systems, because a discrete Schrödinger operator can in some cases be viewed as a spin model, as a quantum spin system on a lattice. So that's interesting, because once you have these results here, you can think, okay, but now take a quantum spin system, which is basically on a lattice, and you can view it on a map. It's not for any spin system possible, but for some of them, yes, as a discretized Schrödinger operator on a finite graph. And then you take the graph limit to infinity, and you can still think, okay, do we get such an estimates for the ground state energy or eigenvector of the spectral gap? What is the asymptotics there? But that's now an ongoing work here. This is also to do with a theory called the generalized locally duplet sequence theory, invented by Serra Capizano in Como. So he basically worked on increasing graphs and discretization of PDEs. So this has to do with the discretization of PDEs. So you can see the Schrödinger operator is somehow a discretization of a PDE in this discrete sense. And that gives you also information about the symbol of this PDE. I said, yeah, this relates to large deviation principle. One can try to generalize this for a bit more general probability measures, a discrete variant of the Feynman-Katz formula. So this is all ongoing works. And so this work was basically done in the winter in Germany, and then it was very cold, a horrible winter last winter. So I wanted to cycle to the university, but as you see, this is not possible. This was my bike, so it was just not impossible. And that was basically one of the days we concluded this, so they remember this, so they make this picture. So very short recap. So we have done here spectral asymptotics for different gamma. For the harmonic oscillator, we get the whole line. For gamma in -1 and 1, we get this more general class of potentials, like the double well potential, for example. This gives a semi-classical regime. Gamma S1, you get just a continuum limit towards this operator. So this is just a Schrödinger operator RD. Gamma is larger than 1. You get a continuum limit of the discrete free Laplacian towards the Laplacian on this. Gamma S -1 is an interesting regime. It gives you a purely discrete harmonic oscillator. So the limit is basically not a limit anymore. The interesting case is the second most interesting case, I would say, is gamma is less than -1. Then again you get a semi-classical limit, but not of a Schrödinger operator in a continuum, but you get a semi-classical approximation of a discrete harmonic oscillator. So this is the regimes we basically studied, and yeah, this is what I wanted to say. If you have any questions, then please let me know. Thank you.
So questions or comment? Okay, wait.
Hi, Chris.
Hey.
Thank you again for your lecture. In what kind of models are you thinking about when you said when it was written that you can apply this to quantum spin systems? In what kind of models were you thinking about?
If you think about this one, you think about the quantum Curie-Weiss model. 1 over n. I mean, this is just, but this notation, I mean, you tensor everything, so this basically sigma 3. It's location I, right? Sigma 3 I, j, and then you take plus what? 1, and I take, so let's say, magnetic field here. I don't know, like this. So this model is this is a quantum spin system which is not directly related, but this model can be restricted. This is a completely mean field. It's invariant under all permutations, right? You can. This is just fully invariant. You can restrict this model. You can restrict this model to a symmetric subspace. So this, of course, on this X a priori on this one, but you can restrict this model to a symmetric subspace. So this symmetric subspace is basically, so this is dimension n+1. There's a computation you can do. This leaves the symmetric subspace invariant. You can restrict it, and you get a matrix of dimension n+1. This matrix associated to this restriction is of this kind of type. It's a tridiagonal matrix. Tridiagonal. If you have a tridiagonal matrix, then you see here a derivative. You see here basically, you know the derivative, the standard derivative in a discretized derivative looks like, I think, 1. Maybe the signs are wrong here. This is the standard discretization of a second order derivative. So this is basically delta, right? Here it's not exactly the same, because here this is a function. This is like a function b, a, b. So this is exactly what I said. This is the second order derivative with a weighted edge. So this is this function what I mentioned here. So the Curie-Weiss model, restricted in the sense, is a discretized Schrödinger operator in which your edges here are weighted by a function, by a suitable function, a symmetric function. And this here is basically a discrete Schrödinger operator. So if you, once you make this correct rigorous, you can try to go to the ground state of this model, which is just a vector. And then you can see, does this ground state localize in such setting? The answer is yes. So this is basically, if you write it down, plus, if you write this completely down and you see how the potential looks like, it looks exactly like a Laplacian with weighted edges plus a double well potential. And then you are a little bit related to what I just said, right? Just here they have weighted edges. It's not like of this type, but the weight. You can try to prove tunneling estimates for this one. You can try to prove what the ground state does. And if you then started with the first, if you started here, Curie-wise, you don't, if you take here the ground state, you have no idea that this basically relates to the thing we studied here. So your large deviations for your ground state are not seen here, restricting it. They remain in the symmetric subspace. You can prove this. You can see it as a discrete Schrödinger operator and apply the machinery here. Once you know very well how to deal with this weights here, and that's now ongoing. How to put the weights here and still get results out of it. And we did it with weights everything once, like standard. But that's the idea about this discretization related to quantum spin systems. So it's one example, but there are more. So they were a good question.
Okay, thank you very much for your talk. I just want to know what's about the fractional Laplacian instead of taking just the Laplacian?
Sorry, could you repeat?
What's about taking the fractional Laplacian instead of taking just the Laplacian? Instead of taking just the main diagonal and the first two, you take something which is everywhere. This is the Laplacian.
Yes, yes.
Okay, there is also the fractional Laplacian, where instead of having strictly positive term on the diagonal and the two small, you have a point everywhere, but there is a decay that depends on the distance between the
yes.
point and the diagonal. They're called fractional Laplacian.
The fractional Laplacian, yeah, that I don't know.
Okay.
There's a good question, but I know this is very interesting, this fractional Laplacian, but this I have no idea. That's a good point.
Just to mention, we are a family of people working on long-range system, and the equivalents of the short-range system are like Laplacian, okay, and long-range system I like fractional Laplacian.
Right, yeah.
Okay, it's just that. Thank you.
It's a good point. Thank you.
More questions? Okay, wait.
Hi, so this is regarding the assumptions on V. Is the purpose of the assumptions in order to guarantee pure point spectrum, for example?
Yes, that's basically what it basically says.
And so you need pure point spectrum all the way up to infinity for everything to work, or could you also handle a situation where you have some finitely many discrete eigenvalues?
So if you take a mixed spectrum, like a continuous part, which maybe you don't care about, and the bound states, which
perhaps I guess it would not come from a Coulomb potential, which you explicitly excluded. But are there examples where you can say something?
Yeah, it's a good point. That's probably this is possible. Probably is possible. So we have discussed this with my colleagues, with Matthias in particular, that in this case you get actually everything, but once you put less restrictions on your potential, then basically your question is, maybe you have just a discrete spectrum, then you get some continuous thing. We don't care about the continuous, we focus on the discrete. To recover it, we think it's possible. But then you should still, your potential should still be kind of, for the first eigenvalues, the discrete ones, should still behave like in this kind of way. What the rest does, I don't know. So we still believe it's possible. We have not elaborated all of this, but that's because then you capture much more models and you just restrict only to the discrete point spectrum, right? So yes, that's something we believe it. Yeah, it's a reasonable question because it's the first generalization basically of this. Yes, you're welcome.
More questions or comments? Oh, wait.
Can you explain a bit more about the difference when you take different scalings? You mentioned that if you take different lambda n and delta n, you obtain different asymptotics. It's not you don't obtain the same spectrum.
Yes, the point is indeed that if you go to take, maybe go back to the formula of the model because it's easier. Where was it now? What was I think here also? So this formula. If you look to this formula, and if you take here, for example, I don't know, delta is here coupled already with lambda, right? Because the prefactor here is this n. It is basically is 1 over delta. Here's my semi-classical parameters. So if you want, you say, okay, let's take gamma equal to 1. Gamma equal to 1, then things, or what was it? Maybe the interesting case is studied. Gamma is -1. Okay, that's maybe an example you want to see. If you take your gamma as -1, then you see that you get basically a factor n squared here and here. You see, you get a prefactor, and this prefactor can be get out of the Hamiltonian just as a prefactor. This prefactor doesn't play any role anymore in the spectrum. So what you then rest with dit operator here. This is just a discrete, fully discrete Laplacian plus a potential. So what you then expect for gamma is -1. You expect a discrete Laplacian plus a potential. You expect this to behave like a discrete model without any semi-classical scaling anymore. Because it's for this choice, this n squared is just a prefactor, doesn't affect the spectrum really, right? So if you scale it down if you divide by n squared, this model is just a discrete Laplacian plus a potential. So you see it very easy if you put a harmonic oscillator here. Then this x divided by n squared, then you get exactly, you reach exactly, basically n squared disk. So disk is in my case just the first this thing here plus x squared. You can show that this is then your thing, and then right. So this is your discrete model. It does not affect anymore. So forget about this. That is the asymptotics of this model is different than having something like n to the power alpha here, or to the power minus alpha, right? It's just different. You get this?
Maybe I refer to maybe in the very first part of the slides when you have a delta n and lambda n.
Okay. What was it? What was it now?
Delta n and lambda n.
Here, you mean?
And you say that if you take, for example, 1 over n, if you take a different way to go to 0, you obtain different.
Yes, there's a very good point. My scaling here is delta is 1 over n, right?
Yeah.
So if you say delta is 1 over n squared, something, go also to 0, then, but this choice of lambda, it changes. You change it. It is the combination of those two choices, those fixed choices, not unique one, the combination of those two choices leading to these asymptotics. If you take delta as 1 over n squared, for example, and you take the same lambda, you get different asymptotics. It is really, it is these combinations fix your model. And this choice, I tried to say it in the beginning, if you take lambda n as exponential of n, for example, again, a different scaling is coming, depending also on the first choice. So this combination fixes basically everything. And we choose this combination because that's kind of, first, but it's a very good point that it's not known why this combination is the one who perfectly gets this, and different combinations are basically not studied. That's a good point.
Okay, and this happens for all values of gamma, because
so if you with this combination, then for gamma in -1 and 1, you get it the results. This is this theorem -1 and 1 for potentials of what was it now? For those kind of potentials here. If you want to extend it for all gamma, so again, this is my combination, this is my fixed choice, and now to get the results for all gamma, okay, then you have to, then we proved it, not only for -1 and 1, but then you have to take harmonic oscillators. You get it for all gamma in R.
Okay.
So that's an extension, but then the prices you pay, you have to consider harmonic oscillators and not, because these are a bit more general. Probably it holds also for these models. For gamma is, for example, -20, but it's more technical. So we didn't add this because it went already. It's very long, so it went already too long.
Okay.
That's why you focus on harmonic oscillator.
Harmonic oscillators. I see.
Thank you for my question.
So let's thank Christiaan again. from PUC-Rio, and he will speak about absence of dynamical localization for long-range Anderson models at large disorder.
Okay. First of all, it's a pleasure to be here. Thank you, you're all organizers, for the invitation. I'll be talking about mostly about joint work with Peter Hislop from the University of Kentucky and Constanza Rojas Molina from Sergi. Here's some acknowledgement for funding, and on that note, I would like to personally thank Rodrigo for, not for the funding, but for all the discussions that he has constantly, frequently raised in the forums regarding the science and scientific development in Brazil. There are many discussions for criteria, for grants and such things, and I think Rodrigo has been advocating for clear criteria focused on quality or over quantity, for example, and this is particularly important. I mean, to have something clear, it's particularly important for people like me who, despite being Brazilian, I studied abroad, spent many years abroad, and I do a kind of mathematics that's not mainstream here, although I hope it will develop more, and it's important to have clear things so that we can at least see where are the keys to open the doors. Maybe we don't have access to the keys, but at least we see where the keys are. So thank you for that. Thank you for everything. It's a pleasure being here. Since the talk is meant for a broader audience, I will leave some references here. I understand it's being recorded, so these are two of the many references in Anderson localization from a mathematical point of view, and the two that when I was a graduate student I enjoyed reading very much, a survey by Gunther Stolz and a book that came a bit later by Michael Eisenman and Simon Varzo. And this talk basically has two parts, part one and part two. Part one, I will introduce Anderson localization, talk about what's the Anderson model, motivations, mathematical results, and part two, I'll talk about the non-local version of the Anderson model and some work that should be posted on arXiv very soon, which is with the co-authors I just mentioned. So the idea is that the physicist Phil Anderson in '58 argued that disorder has a profound impact on the quantum properties of a system. And later Anderson won the Nobel Prize along with other people from his group this is directly from the Nobel Prize page, for fundamental theoretical investigations of electronic structure of magnetic and disordered systems. And since then, this phenomena of trapping in disordered media instead of diffusion or transport is known as Anderson localization. The first mathematically rigorous results are from the late 70s, but nowadays we still have a big open problem in the area and many interesting directions to go. So Anderson localization is a very interesting field. Most notably, the extended states conjecture. It's still an open problem. It's a problem that I think it's problem number one in Barry Simon's list when he launched his list around the 2000s of most important problems in mathematical physics. I mean, there are many important open problems, and each of us has their favorite open problem, so I don't say it's the most important open problem, but it's one of them is a big problem. I'll discuss this in a bit. And I couldn't resist. I only used this slide once in my life, but as I was gathering background material, I saw this and I couldn't put. This is taken directly from Phil Anderson's Nobel Prize lecture. It's available online, and maybe you cannot read, but this at some point he refers to Alice in the Wonderland, which was written by a mathematician, and it says that Alice says, well, in our country, you generally get somewhere if you run very fast and for a very long time, like what we're doing. And then the queen says, a slow sort of country. Here, it takes all the running to just keep in the same place. So hopefully by the end of the talk, this will make a little more sense, but it's taken from Anderson. Okay, I also thank Christiaan for introducing Schrödinger, discrete Schrödinger operators, so you look a bit more natural for my talk. So this is the Anderson model. We'll be concerned with discrete models, although the same problems make sense with some adaptations in the continuum as well. So here is minus Laplacian that was defined exactly in this way before. This is the discrete Laplacian. Here I also have a coupling constant lambda, and I have a random potential v omega. I will explain why random. Lambda will denote disorder strength here. The idea is that the Laplacian models some crystal, and then the random potential will model the impurities that can be present in the crystal. This is a good way to do it. And the lambda is the disorder strength. It will be a fixed parameter for my talk, but it will be taken at some point very large, but fixed. So I'm not taking exactly the limit, but this is the analog would be if I take a little h or a little gamma and put in front of the Laplacian and ask h to be very small. It's competition between transport and the disorder, which causes localization. So okay, this is the Laplacian. The random potential is defined as follows. So you sample a random sequence. You can even think for this talk that you are in a big box, but a finite box. So at this point, we're really talking about matrices. So you sample a sequence of points at random. We fix a distribution that you like here. For technical reasons, I want this distribution to have a bounded density rho, but it makes sense to also flip a coin and deal with singular distributions. It's more difficult because there's less randomness there, but pick your favorite distribution, sample a random sequence, and your potential at point n is simply omega n. Okay, so here we have for each realization of the potential, you have an operator. And the family of such operators, as omega varies in the probability space, is called a random operator. So it's in fact a family of operators. And we're interested in understanding these operators for hopefully almost every omega, which is the case most of the times, but at least for a large portion of the omegas. Okay, so this is what's called now the Anderson model. And Anderson argued, so everybody knows that if you just have the Laplacian, you have transport in your system, absolutely continuous spectrum, and so on. But Anderson argued that once you add a random potential that's sufficiently strong, this changes completely. And as I mentioned, this gave rise to what's now known as Anderson localization, which is the phenomenon that at spectral edges you have localization. We'll talk a bit more precisely about notions of localization in a bit. It will be particularly important because for my talk, we'll have localization in a certain sense, in the spectral sense, but you actually not have dynamical localization when, for the local models as just the Laplacian plus lambda v omega, this is localization is localization. That is not, you don't need many refined notions, they all lead to the same thing. For long-range models, there are differences which I'll discuss. So this is a plot from one of the papers of Svadlana Maibroda, Filochi Maibroda, where they use landscape techniques to plot. But this is just a plot. Here you have the random potential, and here you have the eigenfunction. So the phenomena is basically that the operator spectrum becomes pure point, and so you have, as we'll see, the spectrum is an interval, and the interval is the closure of a dense set of eigenvalues, and these eigenvalues are simple, and associated eigenfunctions decay exponentially. This is three-dimensional. Or one-dimensional. So I'll comment on, there are several situations where you can have this. In 2 dimensions, you can have localization. It's actually predicted to that you have localization for all lambdas. So in 2 dimensions, you should have more localization. For most of the things I'm talking about, I'm thinking of 3D just because of the physical space, but actually most of the things should hold in any dimension, just the regimes should be a bit different. I'll comment about that in a bit. So as a mathematician working in design, what do you want to understand? The first thing you want, I'll use H, but please understand H is H omega, and I want to have things for almost every omega. So you want to understand the spectrum, that's the first thing. And then actually the spectrum is also difficult to understand, but you realize it's not enough to also just understand what's the spectrum as a set. So you need to look at the spectral types and look at the nature of the spectral measures. So this is the second step. And then with the goal that comes from physics to understand if there are bound states or extended states. So if you have true eigenfunctions, or if you don't have eigenfunctions, you have sort of generalized eigenfunctions. Yeah, and I think the best thing to understand is the quantum dynamics, because you actually want to know if you start with a particle somewhere, where will the particle end? This is where things actually come from. Mathematically is the hardest, but this is closely related to understanding the eigenfunctions, existence of eigenfunctions as well. Pure point spectrum, it's sort of the level 1 or level 0 of this process. Once you know that, then you can try to understand more things. So the spectral types should be the first question, and these other two more or less related. So this in dimension greater than 2, this is what should be the phase diagram for this model that I just introduced. I will explain a little bit about the diagram. I mean, it's a very well-known diagram, but just I took the picture from the book that I already mentioned. And what is this diagram says the following. So on the horizontal axis, we have the energies, which is mathematically the spectrum of the operator that we're looking at. So it starts from 0 to 4D due to the way the Laplacian was defined. So you can do a calculation on Laplacian on RD, 0 to infinity. Here is a bounded operator, 0 to 4D. So this is the spectrum of minus Laplacian. And then, as we'll see, when you turn the disorder on, the spectrum increases. And actually, the spectrum is everything that you could possibly get. So you basically have the Minkowski sum of the spectrum of the Laplacian plus the image of the potential, which is scaled by lambda. So you have lambda times the range of the potential. So the spectrum grows linearly with lambda. And so if you make a horizontal line here, that's the spectrum at energy lambda. So it's a bit bigger than the spectrum of the Laplacian, and it grows linearly. So and it goes all the way up to where these lines are. So that's why these lines are there. And the phase diagram at some point, so you start with AC spectrum, and at some point you're supposed to end up in a region where you only have pure point spectrum, and where you have these words that I won't talk about Poisson eigenvalue statistics so much today, but you have Poisson statistics for those who know what it means. It's a signature of independent processes. But I'll talk about dynamical localization quite a bit. So at some point, you have this, and this is actually mathematically proven. So this regime for lambda sufficiently large, it's well understood that you have localization there. And also you have this at spectral edges. So there are very precise curves that you can draw starting for a lambda equals to 0 and then going, and eventually they meet this outside regime. So you know something coming from outside that you have localization. What is not known is whether this part here in the middle holds. At some point I gave a talk at PUC, and my colleague Nicolau Saldanha called this a mushroom, so maybe it's a good name, so I'll call this mushroom. So it's not known if this mushroom exists. I will give all of. I will give all the definitions. My talk will actually be about this because I will basically say that this is a little bit different for long-range models. So I'll give all the mathematical definitions. In a bit, this is just exactly a bit of a teaser, but it's actually not known if you have any of these things here in the middle for ZD. Or say Z3. In dimension 2, it's conjecture that there should be no mushroom. I think this is more or less agreed upon, but maybe not 100% agreed among. But I think physicists are fairly convinced that you should have localization for any disorder strength. Dimension 1 is quite different. I'll say a word in a bit too. So let me give you what I would call a coffee break summary of what's known. So if you're just having a chat with someone, you can pass this message along later. So the spectrum, the questions that I mentioned before, so the spectrum is actually quite simple after you understood it. It's just everything that you could possibly get, you can get. So for example, if you take you sample a potential IID with random variables sample uniformly from -half to half, then you multiply by lambda, and then the image of the range of the potential is minus lambda over 2, and you add to Minkowski sum with 0 for D, you have this, and this is actually correct. This is the spectrum almost surely for the Anderson model. And this is independent of lambda. There is some Borel-Cantelli in the proof and Weyl sequences, so indeed it's a manifestation of some form of Borel-Cantelli. And okay, so you understand this, there is no change as you change lambda. So you go to the next step, and then you try to understand the spectral types, the eigenfunctions, and the dynamics. And this is quite well understood. I'll mention some references in a bit. It's not known, as I said, if you do have a phase transition in D greater or equal than 2, it's not supposed to be there for D equals 2, but it's not known, so I put there anyways. But for D bigger than 3, there should be. There is evidence of that by many works done on tree graphs where this is actually proven, and there's even more recent progress in it. So this phase transition is understood in tree graphs. It should hold here, but no one knows how to do it. Okay, so I will just, now we're done with this was the coffee break summary. So now we'll enter on the actual talk, and I include more details and some more academic things like references. So by now, localization is well understood, although again with several questions at large disorder, so this means taking lambda very large, or extreme energies, which means outside the spectrum of the Laplacian but inside the spectrum of the random operator. And this holds for lambda large in any dimension, but for dimension you have something special, and this holds for any lambda greater than 0. This is basically due to other techniques, things like Kohtani theory and Lyapunov exponents. I will not focus so much about this, but dimension 1 you can imagine is special. But in general, I want to focus in higher dimensions, and the techniques there basically can be split into 2 schools, although nowadays with multi-particle systems and many-body localization and such things, these schools tend to merge together to unite efforts. But originally you had first the multi-scale analysis that started by Froelich and Spencer. There was some previous works in special models, but I'll mention this one first. And later it was hugely developed by Abel Klein and along with several co-authors. Abel is actually Brazilian, and he has many connections with USP. I understand he's a frequent visitor of USP. And here are several of his co-authors. And actually, one of his co-authors, a very well-known paper in this field, is a co-author with Henrique von Dreyfus. I understand he's a professor at USP as well. And the other school is the school of essentially Michael Eisenman with the Eisenman-Molchanov fractional moment method. Ironically, I happen to fall in this other school more than in the first school with the other Brazilians, but as I said, nowadays you need to merge several techniques and ideas from different schools. But this is all very appreciated. And in dimension 1, you have, here are some references for why dimension 1 is special, but I would like to not focus so much on that. So basically you have two different types of techniques, and large disorder is very well understood. The extended states, not so much, but there are several works done in trees. Actually, Abel was the first one to have a proof of AC spectrum on trees. And then there followed several works, Eisenman-Varzo Sims, Eisenman-Varzo, Froese, Hasley-Spitzer. And recently there was a paper by Drogi and Smart. I think it's still a preprint, but there they close a certain thing. Basically, before it was proven that you have, in any interval, you have a C spectrum for lambda small, but now it should be, the spectrum is purely AC. So there is some recent development there, but the extended states conjecture remains. And now I'll enter into the questions of dynamical localization, what it means for mathematicians, and so you start getting slightly more technical, but hopefully not too much. So for example, just to give a flavor of the results, this is a result that you get if you combine, this is not in the Eisenman-Molchanov original paper, but if you combine with ideas from a subsequent paper of Eisenman, you get this result, which says that for lambda sufficiently large, you have dynamical localization. So what is this? So expectations first, you don't need to worry about the expectation so much. This just means my result holds on average over my probability space. What is this quantity here? I'm taking the supremum over T over, I didn't say, but delta 0 is a function that is 1 at site 0 and 0 elsewhere. Delta n likewise. So so this is just the orthonormal basis of L2 of ZD. So what we're doing with this is you start with a particle at site 0, then you time evolve it by this operator, and then you ask yourself, what's the chance that this particle at time t is at position n? So we started at 0, what's the chance that we'll get to site n in time t? This would actually be this quantity square. I have a comment later, but I mean, essentially for here, it's essentially the same thing. And this bound says that for all times, the chance that this particle is found very far is very small. It decays exponentially with the site. So if you go very far, there is a chance that this particle will be there because it's quantum mechanics after all, but the chance is very small. Actually, this bound is, I'll comment some work in progress. This bound is kind of the best you can have in some sense. You cannot go super exponentially or something. There is in a certain precise sense, which I mean is also another work in progress. I'll say a word about this, but this is optimal. In the long range case where you have long range hopping, this will be replaced by a polynomial decay, and this polynomial decay it's also optimal, is what I'll prove in the rest of the talk. But this is the bound of Eisenman and Molchanov. It's the strongest form of single particle localization for these random operators. There are other models, quasi-periodic models, where things are a bit different. But in this setting, it's the strongest you can expect. It can also be achieved via multi-scale analysis, almost all the way up to this. You have any sub-exponential. So you have sub-exponential for any alpha less than 1. So essentially the same thing. N to the power alpha, yeah, n to the power alpha, and then this alpha can be any alpha smaller than 1. So it's almost the same thing, but This is just to say that I prefer to use fractional moments when they apply. They not always apply. A multi-scale analysis is a more broad thing that you see in wave equations. You see is a broader thing. Sometimes fractional moments give stronger results, but the multi-scale just as good too, for example, in this case. And sometimes it's the only tool that you have. Okay. So just one more comment to, if you look at the square of this quantity, this is exactly what I mentioned before, the chance of finding a particle at site n in time t, given that started at 0. And since e to the minus ith is a unitary operator, this is, and it started with something that has norm 1, this is strictly less or equal unless it's 0. But this is bounded by this. So indeed, this dynamical localization has this coincides with the physical meaning. So this is what I commented before. This is very small on average. So the particle is localized. For lambda very large. I want to comment a little bit about ideas. I won't go into proofs here, but eventually I want to give a flavor of what's done and what, as a mathematician, you need to look at. So I'll mention some more mathematical objects. So here is the definition that should have been in the previous slide of delta n. And this is the Green's function. So you take a z outside the spectrum, and then you look at the resolvent matrix elements. This is what we call the Green's function, and there is a good reason for it. If you are familiar with Green's functions from other contexts, but I don't want to comment too much. This is the definition. And this is closely related to the quantum dynamics, as you can see, for example, from formulas like this. I mean, if you think formally of integrating e to the minus ith minus z, you get the Green's function. What you'd want is to actually invert this formula to study the Green's function and then understand the operator. But this is a useful object. You can also think of the Stone-Weierstrass type of theorems. Once you understand resolvents, you can understand more general functions of the operators, and resolvents are much nicer to understand because of several geometrical properties. So just to mention something about fractional moments, once you expand this resolvent, it's specialized to two sites that are equal, m and n, so take m and n to be the same. It's a very easy calculation with the resolvent formulas that Gn and Z has a structure like this. So it's essentially 1 over the potential at site Z, which you should see this tidal dependence in the definition, and minus something that's quite complicated. Obviously, it will depend on all other random variables, but does not depend on omega n. So it's independent of omega n. It's a complex number that is independent of omega n. You can see that since everything here is probabilistic, when this number here becomes a real number, then I might have some resonances in the problem, and we want to bound this Green's function. So there will be some problem regarding that. You cannot integrate this function, for example, even against omega n, because you're integrating 1 over x, and x can be 0, so this is problematic. And fractional moments come to resolve this problem, because integrating 1 over x near 0 is not good, but square root of x, 1 over square root of x is okay. So this was the idea of the Eisenman-Molchanov method, and this gives a priori bounds on the Green's function. So if you integrate over omega n, you have an a priori bound with this dependence 1 over lambda to the s, which you cannot get with s equals 1. And this is what leads to localization eventually through iteration. So there is something called the self-avoiding walk expansion for the Green's function. So to go from the site n to the site m, you pass through all self-avoiding walks. And since you have these local a priori bounds and you have enough independence on the process, basically you can iterate this, and this leads to exponential decay as long as lambda is sufficiently large, because it appears there. This can be improved, and this quote of how large lambda has to be depends on the connective constant of the graph. And you have some very precise things, although not everything is resolved so far, but this leads to exponential decay for these local models. And this exponential decay of the Green's function is enough to establish dynamical localization and to establish, once you have dynamical localization, you have pure point spectrum by a theorem called Rage theorem due to Rel, Armai, Josescu, and Ens. So it's 4 things, 4 people, 4 different people, and Barry Simon arranged the name in non-alphabetical order to call it the Rage theorem, of course. And this states so. You have and then you have exponential decay of eigenfunction correlators, which here you understand this as you have exponentially decaying eigenfunctions. They decay exponentially with respect, so for one realization of the operator, they decay exponentially with respect to a random point, which is called localization center of the eigenfunction. And you can study how this localization center is spread as well, but this is another story. Okay, so this is a flavor, and okay, there is a PDE audience would enjoy more this comment that this iteration process basically reminds you of some subharmonicity statements in PDEs. You have depleted resolving identities, but I think for this audience the self-avoiding walk is better, so I'll just really skip this part. So this was a short overview of Anderson localization, what's known, what's not known for the local case. And the message is that there you can get all the way up to dynamical localization, no problem, and this implies the other things you want to know. So everything is fine if you're just concerned with the localization regime. Now I'll talk about long-range random operators. And you can take, I mean, these models are very natural. It's very natural to start with a fractional Laplacian and to add disorder. From the point of view of the extended states conjecture, which we're very far from proving, but from that point of view, you can think the opposite. You can think, okay, it's very hard to produce extended states in disordered media with a local operator. But what if I add a background that is non-local, so the particle can jump more? I allow for longer jumps. And then I still add disorder, still let this disorder to be very big. But this should help in producing transport, because the particle at any point can jump very far. So it's harder to trap. And this is the motivation for what I'm going to talk about next. So my operators will be of a similar structure as before. So there is a background operator and a random potential defined in the same way with the same hypothesis. But now I will consider long-range operators. So they are indexed by a parameter alpha here that can be any, there will be some restrictions in the theorems, but if you would like, you can think about alpha between 0 and 1. And for alpha between 0 and 1, this hypothesis here, which says that when you write it in a matrix, you have a matrix with polynomially decaying entries. This hypothesis is actually something you can prove for the fractional Laplacian. So the fractional Laplacian, you have a certain kernel, and this kernel satisfies certain bounds. And these are the bounds d plus 2 alpha, so this is summable, and these are bounds from above and below. For the analysis that I'll present later, this is actually what matters. So we don't include just the fractional Laplacian, but any long-range operator satisfying this. So alpha actually being bigger is easier for us. But okay, you can think of just the fractional Laplacian. This is the operator. So instead of having just the local hopping, the particle can go from a site to the nearest neighbor. It can go anywhere, but the chance decays polynomially. Okay, and we want to understand the spectral theory and the quantum dynamics of these operators for almost every omega. There is a huge literature in the spectral theory of these long-range operators. In particular, there is a huge literature on the fractional Laplacian plus random potential from the probability community. And several of these prior references are in previous paper of my co-author Constanza. Here I only list a few, but you can see a few is already like a whole page, and I already left several references out from the random community, so it's impossible to list everything. But what would be known from my point of view? I started working on this problem and I tried to understand what's known, what's not known. The Eisenman-Molchanov paper actually does give you that you have pure point spectrum and polynomially decaying eigenfunctions. If lambda is sufficiently large, you have to work out how large lambda will be and etc. But it does give you that you have some decay. Also, the polynomial decay that you get from there, maybe not the best possible, etc. But that's what I would consider the first result of fractional moments in terms of the long-range operator. It's already there, Eisenman-Molchanov. Then later there was some later interest, and Yaksic and Molchanov, they proved in dimension 1 that you have pure point spectrum for alpha bigger than 7/2 and no AC spectrum for alpha bigger than 3/2. The dimension 1, you can see as before, it helped. So you can get down with no assumption in lambda whatsoever here because dimension 1. But you see the interest from going from the local case to the non-local case is to get alpha as small as possible. Because if you have alpha very, very large, or say you have exponentially decaying hopping, it's known that basically this is the same as the local case. This is not, what is interesting is to get alpha as small as possible. The model makes sense for alpha greater than 0. But we want to see how small, like how sharp these things are. So this d equal 1 here, of course, is a detail, but appreciate in these authors got, for example, results for alpha bigger than 3/2, which is amazing. And then later, Constanza got to this problem. She worked with Martin Gebert, and they proved things like Lifshitz tails, and they actually made precise the bounds for the fractional Laplacian. That these were known from the probability community, but they wrote certain things in a different way, etc. And they did prove this phenomenon of Lifshitz tails, which is that at spectral edges, the density of states behaves differently. So you have very rare eigenvalues there. And more recently, in 2024, this work, the Sartori, Rojas, Molina, Maturana, Escobar, they proved, I apologize, I will define MQ later, but this is the qth moment of the position operator, averaged in a certain way. So they proved that the position operator is bounded. For example, they proved the first moment of the position operator is bounded for this kind of models. What we would like to know is, for example, the second moment or all moments. If all moments are bounded, this is dynamical localization, is another definition. So here, they proved that some moments are bounded, but left open the question on whether other moments are bounded, higher moments are bounded. This was actually a conjecture in their paper that they are not bounded for Q bigger than 2. And then there is some further progress. For example, she has worked in this problem too, proven pure point spectrum polynomially decay eigenfunctions in the spirit of Eisenman-Molchanov, but with multi-scale analysis techniques, and later several other works. And here alpha is in any dimension. Alpha is 165 times d. So these are good results. From the point of view of this talk, I want alpha to be as small as possible. So be a little bit differently, little bit different from this. Okay, and then again, here's the Green's function. As you can imagine, you'll be a little bit different now because we're dealing with polynomial decay. So I'll introduce this quantity here that I know as the Japanese bracket, although I don't know if this is the universal name, just to so that I don't worry about dividing by 0. So I'll add that. I could just say n is different from 0. So the previous result was like this. So you take alpha bigger than 0, s in a certain range, but still less than 1 as before. Then the Green's function decays as before, but now polynomially with this rate. And this is more or less the best you can get here. What we are writing and what we've done, joined with Constanza and Peter, is to get a lower bound for the Green's function instead of an upper bound. We're interested in exactly proving that there's no dynamical localization for lambda very large. So instead of an upper bound, we prove a lower bound. And the lower bound is actually the same as, so you have an upper bound here in this previous work, 1 over s to the d plus 2 alpha. In ours, we prove a lower bound of the same type. We would need to require some assumptions here. So for example, if in one dimension we can have alpha bigger than a half, and one dimension is would be this. I mean, not everything will be consistent for d equals 1. But our result is for any dimension. But for higher dimensions, we need more decay. So alpha, there's a restriction in alpha, but we proved that from below the Green's function is bounded polynomially as well, just like the kernel. And this is something that even for the Anderson model, you don't have lower bounds as far as I know written down. And for this model, we prove that this polynomial decay is essentially optimal for that. So this would be the main result of this proof, of this work. And now I want to talk about dynamical consequences of it. So if I let mq of t be the qth moment of the position operator averaged in a certain way, so this integral here is just because I want to have a formula that follows from Plancherel's identity that relates directly the Green's function to the dynamics. Is another way to see the importance of the Green's function to study the dynamics. But if you're just trying to understand the heuristics, the ideas don't need to care about this whole integral here. You could think of just this expectation. But anyways, if you look at the positions of the moments of the position operator, they are related to the Green's function via this. So the previous result does have implications for the dynamics, which is what we care about. And this is the corollary. So if you look at the long-range Anderson model, for alpha greater than d over 2, there exists a lambda 1. Oopsie. There was a lambda 0 before. This lambda should be lambda 1 and not lambda 0. Yeah, I meant to correct all the typos, but apparently didn't. But because there is a lambda naught but this is kind of good because there is a lambda naught from the localization bound, the upper bound. This lambda 1 is actually possibly larger than the lambda naught. Is lambda 1 greater or equal than lambda naught? We work in the localization regime, and we actually don't know what to do outside this regime, lambda less than lambda naught, even though it should be easier in some sense, but it's not, we kind of need to be in the localization regime to prove delocalization, which is a bit funny, but I can explain more later. But if you are in the regime of polynomial localization with pure point spectrum and polynomially decaying eigenfunctions, actually you have dynamical delocalization. So at some point your position operator becomes unbounded. So for q greater than d plus for alpha mtq is infinity. And this directly infinity is not some power of t that goes to infinity. It is infinity. And here's the proof. So you write down the expression and you use Plancherel's identity to relate the qth moment to the Green's function. Then you can use Cauchy-Schwarz and lower bound I mean, okay, here you just take the infimum, restrict to an interval. This quantity basically, if you restrict to an interval that contains the spectrum, is basically the same thing by Combs-Thomas estimates. Far away from the spectrum, you have exponential decay. So, okay, here you take an infimum, and here you use Cauchy-Schwarz to bound the second moment from below by the S moment, S between 0 and 1, and you use the polynomial decay that you had before. So you have n to the q, so this becomes a minus q here, and then the decay that you had before, it was s to the d plus 2 alpha, so more or less as the Green's function is like d plus 2 alpha. So if you have Green's function square, it's 2d plus 4 alpha, and then the series is infinite as long as as soon as q is equal to d plus 4 alpha or bigger. So hopefully I convinced you that the lower bound on the Green's function implies the absence of dynamical localization for this model. And this is what's new. So we did prove what we thought intuitively, that the long-range hopping would facilitate delocalization. So you still have localization in the spectral sense. Your spectrum is pure point. You have polynomially decaying eigenfunctions, but this shows that something different in the long-range case. Dynamical localization is another story, and it clarifies even more what I think we already knew, that dynamical localization is the hardest to prove in general, and you see that why, because sometimes it won't hold. Okay, so just a few comments. It's also a big responsibility to talk right before lunch, so I definitely don't want to go too much over time or to make you hangry at me, but just a few comments. Yes, exactly, hangry. So you don't. So even though you have pure point spectrum, and I forgot to mention, but our preprint has two parts, and actually one part, the second part, as far as I'm talking about, came later. And some of you maybe have heard talks like last year in the Brazilian Math Colloquium. Connie was here, gave some talks about Poisson statistics. And actually now I joined this, and we also have some improvements on that side. So we have Poisson eigenvalue statistics for alpha greater than d over 2. So you have all signatures of localization except for dynamical localization. You still have Poisson statistics for this model, and it's particularly nice that most results require some condition like this. Actually, this is the same condition that we require for the other results. So it's d over 2. I told you that I want to get as close as possible to 0, but there's supposed to be some phase transitions there as well, which I didn't have time to talk about. But d over 2, I conjecture is more or less optimal for certain things, for example, for Poisson statistics. But my co-authors, I don't know if they conjectured this, I didn't. But I think from the technique that we use, it's pretty clear that you can only get to d over 2. You need to come up with something else. This is actually, this Poisson statistics was proven first for Anderson models by Minami. He was in Irvine at the time, and there's this famous Minami estimate that comes into play. Anyways, but these models, although they have all the signatures of localization, they don't exhibit dynamical localization. The proof, you might wonder what happens for the Anderson model with some techniques that we have, and actually this proof does give you what I said before, that the exponential decay from Eisenman-Molchanov is actually the best you can get in some sense, in the sense that even for the local case, there are some sites where you can prove that from 0 to n you do have a lower bound e to the minus n on the dynamics. But in a certain sense, you have to be careful, average certain things, and I don't have time to talk about this. This is actually another work in progress with a colleague from UFRJ, Sergei Sergeyev. And in my abstract, I did mention that if time allows, I'll talk about some work that actually is preprint, that's joint work with Moacir Aloysio, César de Oliveira, Derberton Oliveira, Mariane Picossi. But there's no, as you can see, there's no extra time, and it was clear to me when I was preparing my talk because I wanted to give the background. But this is already on arXiv, so you can just read. This is about properties of long-range long-range Schrödinger operators, but not necessarily random. In fact, quite structural properties connecting exponential polynomially decaying eigenfunctions and the dynamical localization and equidistribution of localization centers, many things. So I wanted to mention this, and I want to just say that from a technical point of view, we do use the Eisenman-Molchanov approach, but we need to get lower bounds. And those who thought about things like unique continuation and such know that lower bounds are typically quite hard to achieve, and you need to do certain things. So we managed to prove an a priori lower bound on the diagonal elements of the Green's function. Actually, you need an a priori lower bound in this more precise fashion here. And this is our main ingredient. We do use the self-avoiding walk expansion. And the idea is that you have, from 0 to n, you have one long jump of the particle, and then the other jumps you need to visit other sites, and the Green's function by the a priori upper and lower bounds that we know you have, it's basically like 1 over lambda. So if you have less jumps and lambda is very large, this sort of dictates what the decay should be, and this is expressed here in this picture. So the red path here is the shortest path. From 0 to n, you can go directly in one jump. And the operator has this decay, polynomial decay, and this basically is what dictates the lower bound for the Green's function. And then you have many other paths, but you have to visit other sites. And then what happens at the level of the analysis is that this shortest path gives you a 1 over lambda square, and the other paths give like 1 over lambda cube, 1 over lambda to the 4th, etc., etc. So if lambda is very large, you can absorb. They give with the same coefficient, same dependence on n, so everything needs to be very precise, but they do give a smaller contribution, so you can use the triangle inequality by subtracting things. And so there is some detailed analysis that needs to be done there, but this is the idea, this is the picture, and coincides with the physical intuition that we had at the beginning. So this was quite pleasant. And with that, I thank you for your attention.
Things like this random walk expansion, people also use for correlation functions of spin systems. To what extent are there parallels or conjectural parallels between, like in 2 dimensions, there's Merman-Wagner theorem saying there is no magnetization. The conjecture is there's no localization in 2 dimensions. It feels similar, but is this really accidental, or is there something deeper underneath?
Thank you for your question. In fact, there's no coincidence in this, although sometimes, as was mentioned before, you can take results from discrete Schrödinger operators and immediately apply them, or sometimes not immediately, but with some ideas, and apply them to spin systems. This was done for random operators and random spin systems before. For example, we have the XY spin chain. Now there's a lot of work by Abel and etc. in the XXZ spin chain, and there you have an n-particle random operator. So you have many such immediate connections, but here I should mention that many analogs from many of these results come as analogs of theorems or criteria from statistical mechanics, mainly due to Michael Eisenman, I would say, although he's not probably the first one that looked at the random spin system and etc. And maybe he hasn't actually done stuff in that direction. But for example, that we have a finite volume criteria for localization in random operators that, as I understand, he told me, comes exactly from something in statistical mechanics. You have your Green's function in a finite box is less than 1, has this behavior, then it must decay exponentially. Exactly. So you have this, and you have many other things. For example, Schenker has a bound for how large. He has a paper called "How Large is Large," which is like how large lambda needs to be for you to have localization. This paper confirms Anderson's original prediction, although actually it may not be the optimal, well, even what Anderson predicted, but there you have a self-avoiding, you have the connective constant, and the proof uses self-avoiding walks. So we don't know what the connective constant is on ZD, I believe. We have very good bounds, and this connective constant enters there as well. And you have this expansion. So this is another instance. So outside, maybe even if you don't have the rigorous connection, but the connection at an intuitive level and the way of thinking, I think this community has benefited a lot from these interactions with statistical mechanics, probability, etc. So yeah, thank you.
More questions?
I hope this is not a naive question, but as I understand, the meaning of long-range Laplacians in your talk refers exclusively to discrete or lattice models. Is that correct? And
for this talk, yes.
And if you were to extend this kind of notions, let's say because the methods are using Green's functions, right? So let's say for Schrodinger, ordinary Schrodinger operators, are they considered long range in this?
Yeah, in the continuum, yeah. I think
so ordinary Schrodinger operators, if the ordinary Laplacian is considered?
No, not the original Laplacian, but if you take the fractional Laplacian. Right. For example, you can think of the fractional Laplacian as you can do what we do here, which is basically you do functional calculus and take a power of the Laplacian. But you can also think of it, and it's pretty important for PDEs, regularity theory, etc., as a integral differential operator. And then you start with something like a discrete quotient. You take an integral, you take a principal value, or with the equivalent different definitions without the principal value. But you take it as an integral differential operator, and there, even if you want to calculate this Laplacian at a function at a point, you need information over the whole space via this integral. It's an integral in Rn of a difference quotient. So the fractional Laplacian would be non-local. The original Schrodinger is also local because the Laplacian is a local operator. You have a comparison principle, many things in that sense. But the fractional Laplacian still makes sense in the continuum. Everything actually makes sense in the continuum here. It's just that technically it's more difficult because the operators are unbounded, and physically it makes a lot of sense to consider discrete problems, so we look at discrete. But
the other question is in the continuum model, that in the Landau model, for example, in 2D, I think Abel, Klein, and so on, we're able to show at like the core of Landau levels do not encounter dynamical localization.
Yes.
That's why they can contribute to.
Yes, in fact.
So is that mechanism? Because I don't know the details of their proofs. Is it related somehow to at some mathematical level?
I would say
so. Or it's completely independent.
I would say this, for example, this one of, I think Abel has several works. One of them was an Annals paper, eventually. And so I think the mechanism there is more subtle. You have these Landau levels, and you have these gaps. Like it's a different story here. We have a lot of questions that I hope we can answer with techniques that come from these previous works that prove the dynamical delocalization in very, very difficult scenarios, or that prove AC spectrum on trees. The AC spectrum on trees happens because you have a tree that grows exponentially and you have these resonances, and somehow this exponential growth allows this delocalization. I think technically this is not nothing like that. And we already have this long range that facilitates, although I'm not going to say what we did is easy, but if you understand fractional moments well, there is already something, it's more something like that. But everything needs to be a lower bound. But there are many other questions, as in, for example, do you have extended states outside of the localization regime? Or if lambda is smaller, or if alpha is smaller, there's supposed to be some phase transition there, actually. And we hope that we can get some hints on how to to work with that due to these other works. But it's not. I would say this is a little easier than what was done in that paper.
Thank you very much. A view on Anderson localization from a completely different perspective. So for me, the localization a bit reminds, say, the Shor algorithm on quantum computers. So you also have certain peaks which appears from nowhere. I believe that this is a different mechanism. Yes, but do you know, have you heard about using of Anderson localization as something like quantum computing applications?
For quantum computing, I have not heard, although there is flavors of certain things that we use, but it's more the dynamical side. My PhD advisor, Jeff Schenker, he has been working with someone, Ramiz Movasa. He's an IBM researcher, I believe still, and it's towards quantum computing, but it's much more dynamical. So maybe it's more related to your other interests as well. So I haven't, it will be interesting to know this, but this is specific thing you're asking, I haven't heard about, so maybe we can have a chat about it.
Thank you.
Thank you.
So more questions or comments? No.
So I'm gonna ask a question. First, thank you for the talk, but I'm gonna ask a question that's coming from a place that is the non-random Schrödinger operator. So I don't know if it directly translates here. You obtained a lower bound for the green function, and do you have more information? In principle, this tells us that the spectrum can be absolutely continuous, but it can also have a presence of singular continuous spectrum as well, right?
Actually, in this case, we still have pure point spectrum.
Okay.
Because the lower bound is not enough to. It's a lower bound that is the same as the upper bound on the localization regime. It's a bit different. You still have some ability in some sense. It's not, if you're thinking of the criteria, the Simon-Wolf criteria, you don't have an infinite sums. Still, all the sums are finite. But what you're asking is basically about if you can have singular continuous spectrum or not. So in dimension 1, there's supposed to be a phase transition from alpha between alpha bigger than a half and alpha less than a half. Our results apply for alpha bigger than a half. But actually, because of this conjecture, it should be easier to analyze the case alpha less than a half. But we don't have many tools to work with that. So yes, we are thinking about it to analyze even the other models that are not necessarily random with these techniques. But so far we make a critical use of the randomness here. But you're supposed to have some phase transitions, and maybe even for the random case, who knows, alpha equals a half, maybe you could have some singular continuous spectrum. It's unclear. But the conjecture is that below half you should have AC spectrum, and above pure point spectrum, so maybe alpha equals a half. Yeah.
Okay, thank you.
So I have a question, but everybody will kill me if I ask. So I will ask after during the lunch. So thanks, speaking again.